Hello everyone, we are on page 19, so make sure you're following along and taking notes as we go, and then when we have class I'll be checking in on those notes. Alright, so there's an equation that we're working with. There's actually going to be two, and the first one is Q, which is heat, is equal to M for mass, C is heat capacity, and delta T, this is a change in temperature. And so there's two ways that we're going to be calculating heat. One is using this equation, we call it, well, I've heard many people call it MCAT, so M and then like a CAT to help them remember. And then we have another one we're going to use, which uses a delta H, and it's usually moles instead of mass. So we usually have the moles of something and then times by a delta H, and it's either of fusion or vaporization. More on that in just a moment. So we're going to see this transfer of heat. Like if I have this coffee cup calorimeter, so we have our styrofoam cup here, and I'm going to take a little square of metal, and let's say that this metal is at a certain temperature. It's really, really hot, and we're going to place that metal inside of the water. Okay, and inside this water we also have a stirring rod, so the water's moving around, and we have a thermometer. Well, the heat from this little metal sample here is going to leave, it's going to go out towards the cooler water. Okay? And what's really cool is that this heat, the heat of the metal, is equal to the heat that's going to be absorbed by the water. But reminder, if it's leaving the metal and then it's absorbed by the water, these two are the same magnitude, but they're opposite in sign. So we'd have like negative heat because it's being lost by the metal, and then positive heat that's being absorbed by the water. And they're equal in magnitude. Okay, so if I can figure out one of these, then I can solve for the other one, or vice versa, but be mindful of the plus and the minus. So if our metal was the system, then that would say like the heat of the system will equal this exchange. The heat that was lost by the system, so let's do a negative, has to equal the heat that was absorbed by the surroundings. Great. So one way, like I told you, that we can calculate this heat, so this heat that let's say is lost by the metal, if you take the mass in grams of the metal, and then different elements have different heat capacities, and so we'll have a list of that. So you're going to find the heat capacity, and then it's the change in temperature of that metal. Okay, so it's delta T, and reminder, delta is final minus initial. But what temperature should we use? Because I said grams here, and honestly when I was first prepping these notes I couldn't remember if it was Kelvin or Celsius. But here's what's really cool. You're going to be given the heat capacities. Okay, like you're going to be told, and you don't need to turn the page just yet, I just want to show you this. You're going to be told what the heat capacity is, the number and the units. And notice how it says, this one says joules per mole degree Celsius, and this one says joules per gram degree Celsius. So if I'm dealing with mass, it's going to be in grams. Joules is energy, and then we must need it to be in Celsius, not Kelvin. If instead of mass in grams, it looks like we could also use moles. So we're going to have temperature, which is going to be in degrees Celsius, the specific heat capacity, which was joules per gram degree Celsius for your units, and then you're going to be left with final energy in joules, not kilojoules. So see, joules, grams, and Celsius. All right. A 97 gram iron bar. So the mass of the iron is equal to 97 grams, was heated to this temperature. So the temperature initial that we're starting with for the metal is 143 degrees Celsius, and placed in a styrofoam cup calorimeter containing, so mass of the water is 350 grams. Hey, just a reminder, water has a density of, so the density of water is 1 gram per milliliter. So that means that 1 gram of water is the same as 1 milliliter of water. So if they ever tell you this in milliliters, you can change it to grams. Okay. At 25 degrees Celsius. So the temperature initial, so this is temperature initial of the iron. This is temperature initial of the water. 25 degrees Celsius. Great. The maximum temperature of the water was measured to be, all right, so after we added this metal into the water, it raised the temperature of the water. And this final temperature of the water is 28.40 degrees Celsius. But we've also reached thermal equilibrium. So when the water stops increasing in temperature, the iron stops decreasing in temperature. And so what's really cool is this final temperature is the case for both the water and for the iron. Their final temperatures are both 28.4 degrees Celsius because they've reached thermal equilibrium. How much heat was gained by the water? Okay, so Q is equal to mc delta T. I know what the mass of the water is if I can get the specific heat of water. I know what the temperature final and the temperature initial is. I'm just going to check really quick. On page 22, we have this big list here, and I have water. So this is negative 10 degrees Celsius, or think of it more like solid, like ice. And then 25 degrees Celsius, and so like this is more like liquid. And then this is boiling, this is gas. So instead of 25, it's like liquid water, which is what we're dealing with, has a specific heat capacity of 4.18. So the heat capacity of water, liquid, was 4.18. and joules per gram degrees Celsius. So if I want to know the heat gained by the water, then I can plug in everything I know here. So of the water is mass of the water times by the specific heat of the water, and then times by delta T, which is temperature final minus temperature initial, so 28.40 degrees Celsius minus 25 degrees Celsius. Okay. Plug that in my calculator really quick. 350 times by 4.18. Now, I need to put this in parentheses for the final minus the initial. So temperature final, 28.4 minus my initial, 25. And we get 4974.2. Grams cancels, Celsius cancels. We're left with joules. Okay, not kilojoules, joules. And then sig figs. If I look at like the items here, this was 1, 2, 3, 4 sig figs. This was 3 sig figs. Oh, when I subtract these, this should be digits after the decimal. So 28.40 minus 25.3.400. When I subtracted those, 3.40. So that's 3 sig figs. So if this was my final answer, I'd round it to 3, so 4,970 joules. Great. How much heat was lost by the iron? Okay, so here's the cool thing. All of the heat that was lost by the iron was absorbed by the water. So I could just take iron. It's the exact same amount, except it was lost, so it's negative. So it released 4,974. 4,974.2 joules. And again, if this was a final answer, then I'm going to round that. 4,970. Negative, though. And then, what is the specific heat of iron? So, if I go to my list, I can probably find it, but what if they don't tell me? I know what the Q value is for iron, and I know it's going to equal MC delta T. And I know what the mass of iron is, and I can figure out delta T. So I'm going to divide this. So if I take the Q of the iron, divide it by the mass, and then the delta T, which is temperature final minus temperature initial, that will equal the specific heat. Okay, so negative of this number divided by parentheses the mass of the iron, which was 97 grams, times by the temperature final for the iron, 28.4, minus temperature initial of the iron, 143. Okay, and then divide that, the specific heat, and then I'm going with 3 sig, oh no, actually 2, because 97, yeah, 97 grams. So without sig figs, I have 0.44747, etc., which would be about 0.45. And we can see the units, but we also know units of specific heat. This was joules, and I'm dividing it by mass, which was grams. And then Celsius minus Celsius is Celsius, so degrees Celsius. So we calculated the heat absorbed by the water. We know that it's the same amount of heat that was lost by the iron, so we put a negative sign. Then we use the same MCAT equation to get the specific heat of the iron by dividing those, and I put that in. Great. All right. So, sometimes instead of grams, you're given moles. Okay. So we have temperature in Celsius still, joules, but then I want you to use the specific heat capacity that's joules per mole degree Celsius instead of grams degree Celsius, because you're given moles. And so it's really important to look at what is provided for you. Like I told you, sometimes they're going to give you a specific heat that has grams, and so your mass needs to be in grams. Sometimes they may give you a specific heat where it's moles, and if you're not already in moles, you might have to go to moles. Like if they give you grams, you might have to do a one-step goalpost to get to moles. So a quick example of this. The specific heat capacity of gold is 0.129 joules per gram. Ooh, Kelvin. Interesting. So my temperature should be in Kelvin, not in Celsius. We're finding the molar heat capacity. So that would be how much heat is gained or lost per mole. If 743 joules of heat are added to that many moles. Okay. I want to see joules of heat is added to this many moles. And so they gave us the grams per mole. We're going to solve for this, but we want the mole one. Interesting. We have the heat of the gold. The symbol is AU. If this many joules of heat are added, okay, so 743 joules, and the amount of moles for the gold is 3.4 moles at 2 degrees Celsius. Okay, so temperature initial, because it's saying what's the final temperature, so 2 degrees Celsius. We're solving for temperature final. So we'll come back to A in a moment. Let's look at B. We're solving for temperature final. They've given us moles though, and then we have a heat capacity that's in grams and it's in Kelvin. And so what I actually would prefer to do, instead of trying to convert this to moles in here, it's going to be so much easier converting this moles to grams. And that way I can use what it's given to me. Also, there's Kelvin, and so I'm going to have to make that shift here as well. And our final answer will be in Kelvin, not Celsius. Okay. 3.4 moles of gold. Moles of gold, grams of gold. All right. Periodic table. The periodic table for AP Chem says it's 196.97 grams per mole. 3.4, wow, big chunk. 196.97, 669.98 grams. All right, so now I know the mass. I'm solving for temperature final, and I know that my heat capacity for the gold is 0.129 joules per gram Kelvin. So I'm looking at these units, and I'm making any changes that I need to. So I had moles, so I convert it to grams. I have Celsius, so I'm going to convert it to Kelvin. So that would be 275.15 Kelvin. Great. Watch carefully how I rearrange this equation because it can be a little confusing for students. So I have Q is equal to MC delta T. Okay. We're solving for temperature final, which is in here. So I'm going to start by isolating this delta T by dividing the mass and the specific heat. So Q divided by M and C will equal delta T. Now, a reminder, delta T is temperature final minus temperature initial. And I'm solving for temperature final. So the last step will be adding temperature initial. So heat divided by mass that's multiplied by the specific heat capacity plus the temperature initial, that's going to equal my temperature final. All right, plugging this in my calculator. So 743 divided by mass, which was this number. Oh, there you go. Mass, which is that number, times by the specific heat capacity, 0.129. And then after I get that, I'm going to add the temperature initial, which is 275.15. So my final answer in Kelvin is 283.75 Kelvin. Alrighty. When I convert it, when I want the 2 degrees Celsius, that would give me like 3 sig figs. Like I have no digits after the decimal. I have 2 digits after the decimal. This is 2 sig figs. So I would do final answer 280 Kelvin for my final answer. Alrighty. We will practice this more, but we gotta jump ahead. So, here's what I need you to know. This is a phase change diagram. We're on page 24. And so what we're seeing here, like let's pretend it's water for a moment. At this low temperature, we are going to add energy. So like from here to here, like let's put it on a hot plate. So I'm going to add energy. And when I add that energy, the temperature is going to increase. And so this is not a phase change. This is like the solid, so it's like ice, and the molecules inside there, they are like moving a little bit, and then they start moving more. But they are not going to a liquid yet, okay? So they're like moving slow, and then we're adding energy, and they're moving more. But it's still a solid. So solid from A to B, it's a solid. Now, whenever we have these diagonal lines, that is when we use the MCAT equation. So like here would be the Q is equal to MC delta T. Okay. Same for this guy, and same for that guy. Now, this is the phase change, and this is what's so crazy to me, is we're going to still add heat. Like, look, we're still going to add heat energy, but the temperature doesn't go up. Where that energy is going is towards breaking IMF. So this is where we're transitioning from a liquid to a gas. So, a solid to a liquid. Oh my God, a solid to a liquid. We're melting. A solid to a liquid. So this is, if we're going this direction, this would be melting. If we're going the opposite direction, this would be freezing. 2 E's. Freezing. So, completely solid, completely solid, completely solid. Now it starts to melt. Now it's completely melted. Liquid just increasing in temperature. And then it starts boiling right here. So this is a gas over there. If we go from here, this is boiling, or vaporizing, whatever you want to call this, and going from a gas back to a liquid is condensing. Okay. All right, great. Now, we know that on the diagonals, when it's fully a solid, liquid, or a gas, that we're going to use the MCAT equation. But what about these phase changes? So right here and right here, and that's when you use the amount of moles times by the delta H, okay? Now, if it's this part, we call it a delta H of fusion. And if it's this part right here, we call it a delta H of vaporization. When you're going to a higher energy, so if you're going from the solid to the liquid, use the positive version of this number. If you're going from a liquid to a solid and you're losing energy, use the negative version of this number. Same magnitude, just opposite in direction, like positive versus negative. Great. Okay. One last thing. You need to know the temperatures in Celsius at which water boils and freezes. So, freezing happens for water at 0 degrees Celsius, and it starts boiling at 100 degrees Celsius. All right, great. Okay. We're going to do one last example, then we're going to be done, but I'm going to add something to this, so listen carefully. The question is, how much heat is required to melt a 5 mole pure sample of ice? And I want to change this. So we're going to melt this, okay? And let's say starting at negative 20 degrees Celsius. And so how much energy is it going to take an ice cube that's starting at negative 20 degrees Celsius until it's completely melted? So if I think back to that phase change diagram, what I am saying is we're going to start at negative 20 degrees Celsius, and we need to add energy until we get to 0 degrees Celsius, and it's going to start melting. I'm going to call this Q1. And then I need to, even though the temperature is not going to change, I need to get from 0 degrees Celsius to completely melted. Like, this is where it just barely starts melting. This is where we stop melting. So this is my ending point right there, and I'm going to call that Q2. So for Q1, I'm going to use MCAT. Q1, I'm going to use MCAT. All right, so that's going to be the mass of the water. Oh no, it's 5 moles of water. So let's do a quick change to that. Ooh, unless I have the molar enthalpy. Yeah, I think so. That would be convenient. So we're dealing with solid water right now, not liquid. And so this is 2.11 joules per gram degrees Celsius. I'm on page 22 if you want to know where that's at. This is 38 joules per mole degrees Celsius. So how about I grab that guy? That would be so convenient. All right. So the amount of moles is 5 moles. The specific heat was 38, and this was joules per gram, or not gram, moles Celsius. Okay. And then temperature delta T, temperature final minus temperature initial. So my final temperature for this leg of the journey is 0 degrees Celsius. Minus the initial, which is, so minus the negative 20 degrees Celsius. All right, so 5 times by 38 times by 0 minus a negative 20, so times by positive 20. So this equals 3,800 joules, not kilojoules, joules. Now, I know that this is going to be helpful in a moment, so if I convert it to joules, then that would be 3.8 kilojoules, if I convert it to kilojoules. For the next leg of my journey, Q2, I'm not using MCAT. I'm using the delta H of fusion, okay? And I'm going to do a positive of this number because I'm melting. I'm gaining energy. I'm going from the solid to the liquid. So I'm going to take the amount of moles, which was 5 moles, and I'm going to times it by the delta H of fusion, which is 6 kilojoules per mole. So what's cool to see here is that we know that moles are going to cancel. Okay? And so then this would be 30, isn't that huge? 30 kilojoules. Wow. Okay. So So it took way more energy to melt this than to raise that temperature on the first leg of the journey. My final answer to know how much heat energy it took to melt ice, completely melt ice that started at negative 20 degrees Celsius, my Q total is Q1 plus Q2. That's why I converted it here, because I knew I was going to end with kilojoules there. And I need these to be in the same unit. So then I'll have 3.8 kilojoules plus 30 kilojoules. And so I'll have 33.8 kilojoules. Okay. I am going to round this to 1 sig fig. Oh, that drives me nuts. So 1 sig fig, 2 sig figs, and so that is approximately 30 without a decimal kilojoules. Positive. I had to add that much energy in order to raise the temperature of the ice and then melt the ice. All right, everyone, thank you so much. We will keep working on this during class.